Now that we have discussed about the properties related to parallelograms, or any two figures on the same base and between same parallels are always equal in area. So in the previous session we have seen two parallelograms which are on the same base and between same parallels are of same equal area, however far or however near they are between the parallel lines. But the condition, the base must be same and they must be between two parallel lines. Now let's see if the converse holds true. Given that two parallelograms lie on the same base and given that the two parallelograms are of equal area, now the investigation comes on whether these two parallelograms lie between same parallels. So let's see if the condition of same base and equal areas of parallelograms gives the learning outcome that they are between parallel lines, or that the outcome conclusion is that they must be between parallel lines. So let's see in brief. Before we see the investigation of the converse of the previous theorem, now comes the introduction of area of parallelogram. So let's see area of parallelogram, the area of the planar region called a parallelogram, opposite sides parallel and equal. Area of parallelogram. What is area of parallelogram? Just like area of triangle is half into base into height, and area of rectangle is length into width, similarly area of parallelogram has its own specific definition. Let's see what is the formula we can derive for area of parallelogram. So let me take a parallelogram ABCD. Out here. So here is my parallelogram A, B, C and D. And let me drop a perpendicular from D such that this forms perpendicular and this is the height of the parallelogram. So this is called the height of the parallelogram. So in parallelogram ABCD, the symbol for parallelogram is this. So in parallelogram ABCD, now I take the base which is on the bottom of the parallelogram, that is AB is the base of this parallelogram. AB is the base, is how I understand the base being AB. So let me denote the base with some B units. Now comes DE. What is DE? So here from D, drop a perpendicular to AB. So from D, if I drop a perpendicular to AB, which cuts AB at E, which cuts AB at the point E. Now clearly we know that DE is the perpendicular, that is DE is the height of the parallelogram. So AB is the base of the parallelogram and DE is the height of the parallelogram. So base denoted by B, of course height now denoted by H. So we have the base and the height for the parallelogram ABCD. So AB is the base and DE is the height. B stands for base and H stands for height. Now let's see the area of the parallelogram. So here we have a formula which says area of parallelogram ABCD. It can be meter square, it can be centimeter square, it can be kilometer square. Now let's come back to the converse of the previous property. Triangles on the same base and between same parallels are equal in areas. And parallelograms on the same base and between same parallels are equal in areas. Now the converse of that theorem. So how do we define the converse? So let's state the converse. My question is, will parallelograms on the same base, which are on the same base, and having equal areas, the two parallelograms or any number of parallelograms on the same base and having equal areas lie between is what I have a question as converse. Will parallelograms on the same base and having equal areas lie between the same parallel lines is the biggest question out here. So let's see the converse of the previous theorem. Investigating the converse of same bases and same parallels. Now let's take two parallelograms with the same base and lying between two lines which are not parallel. So the converse clearly says that if I have the same base AB and if I have two parallelograms lying, let me say there's another line L which is not parallel to this but a bit away from the base AB. Now let me take two parallelograms in this case. So one of the parallelogram is formed by the line L, which is A, B, C and D. So A, B, C, D is a parallelogram which is formed with the base AB and the line L. So here is the parallelogram. Now with this parallelogram, let me take another parallelogram which has the same equal area. The condition for converse is that they lie on the same base. So taking the same base AB, I'll draw another parallelogram which has equal areas and same base. So let me take another parallelogram of the same equal area between the line L and the line AB, the same base AB. So here is the same base AB. This is the same base. So therefore, I take another parallelogram out here, AB, EF. So here I have another parallelogram AB, ABEF out here. So here is the parallelogram ABEF between the same base AB and between the line L and the base AB with equal area. So here ABCD and ABEF are the parallelograms on the same base AB, which is out here, are parallelograms on the same base AB and between the lines L and same base, and between the line L and same base AB. So between same base and the line, there are two parallelograms ABCD and ABEF, which are equal. Also, area of parallelogram ABCD equals area of the other parallelogram, which is ABEF. So area of parallelogram ABCD is equal to area of parallelogram ABEF. So you have taken parallelograms having equal areas as per the converse of the statement. Now, when in such case of two parallelograms lying on the same base and with equal areas, will the lines be parallel? Is the question out here. The converse of the theorem clearly says, as supported by mathematics, that they must be parallel. Two parallelograms lying on the same base and which are in equal area must be between the parallel lines. That is, this must be equal to this. Is how we understand the converse of the theorem. So here, that implies the line L is parallel to the base AB. So we have a property which says triangles, parallelograms on the same base and with equal areas must lie between the parallel lines. That's how we understand the converse of the previous theorem. Converse holds true in this concept. Two parallelograms between two parallel lines. Now that we have discussed a property relating to the parallelograms, parallelograms on the same base and between same parallels are equal in areas and even the converse holding true. Now comes the question, what happens if I take the case of a triangle? Triangles on the same base and between same parallels, will the areas be equal? Is what we are going to investigate. The same theorem now investigated for triangles on the same base and between the parallel lines. Let's investigate the property for triangles. Before we do that, let's understand the triangles which lie on the same base. Let's try to just recap with what we have learned. Triangles on the same base. So here, let me try to understand how the triangles look between the same base and between same parallels. Imagine I take the same base, which is AB, just like in the previous case of a parallelogram. So with the same base AB and between the parallel line L, let's say this line is parallel to the same base AB. Now let me draw two triangles which are with the same base AB and which are between the parallel lines. So here I have a triangle, say from here to here. That's how I get one triangle which is like this. So this is the triangle, the first triangle which connects the line L with point C. So ABC is a triangle with the same base AB and between the parallel line L and AB. So let me take one more triangle in the similar manner. Let me take a triangle which is far away. So this is out here. So I have the other triangle which connects with D. So this is the triangle ABD, which is on the other side. Now as we see the two triangles, this triangle is on the base AB and the other triangle also on the same base AB. So here AB acts as the same base and they are between the parallel lines L and AB. These two lines are parallel. So triangles on the same base and between same parallels look like this. Now the investigation comes to prove whether area of this and area of this are equal. So we are going to see how we can connect the areas of these two triangles which are on the same base and between same parallels, investigating the property for triangles. So let's see the property. So triangles on the same base. So if I take the statement for same base theorem says that triangles on the same base and between same parallels are equal in area is how we understand the same base theorem. So same base theorem says that if two triangles are taken on the same base and between same parallels, they are equal in area is how we understand the same base theorem connected with the property. So when I take two triangles between same base and same parallels, just like this, A, B, this is the line L, and I have a triangle like this, then the two triangles must have equal areas. So area of this triangle must be equal to area of this triangle is how we understand the areas. That is, AB being the same base, if AB is the same base, and L is parallel to AB, if the two lines are parallel and L is parallel to AB, then area of triangle ABC must be equal to area of triangle ABD. The area of the first triangle must be equal to area of the second triangle. Is how we understand the area of two triangles being equal when they are on the same base and between the same parallels. Is how we understand the property of two triangles with the same areas, between same base and between same parallel lines. Now that we have discussed the property of two triangles on the same base and between same parallels are equal in area, now comes the question, what if there are more than two triangles? Well, all the three triangles will have equal area. Today's session is about triangles on the same base, with the question, what if there are infinite triangles? What could be the case if I draw more than two triangles? Will all the areas be equal? Let's investigate with the property. So now that it is based on more than two triangles, let's take the case of at least 3 or 4 triangles between the same base and between the same parallels. So here I have the base AB and there's a line which is parallel to this. Now between the same parallels with the same base AB, let me take more than two triangles. Say for example, just like in the previous case we have taken two triangles, now I take many triangles between. Triangle number 2, triangle number 3, triangle number 4. So here I have totally 4 triangles as given by this. The first triangle is ABC. So totally I have 4 triangles which are taken with the same base to be listed out here. The first triangle is ABC and the second triangle is ABD, as can be seen in the diagram, and the third triangle is ABE, as seen out here. And the fourth triangle is ABF, as taken here. So these are the 4 triangles which I have taken with the same base AB and between the parallels L and AB. So we have more than 2 triangles, that is 4 triangles out here with the same base AB. Interestingly, for all this, AB is the common base for all the 4 triangles considered. So according to the property, 2 triangles on the same base and between same parallels are equal in area. So when I take the first 2 triangles, the triangle area of triangle ABC must be equal to area of triangle ABD. Now when I take the case of the second and the third triangle, these 2 triangles are on the same base and between same parallels. So area of this must be equal to area of this. So with the second case, area of triangle ABD is equal to area of triangle ABE. Next, now since these 2 triangles are on the same base and between same parallels, ABE and ABF must have equal areas, as seen with 2 triangles on the same base and between same parallels are equal in area, the property as discussed in the previous session. Therefore, area of triangle ABE equals area of triangle ABF is what we see when I take the first 2 in pairs, then the second 2 in pairs, then the last 2 in pairs. So I have totally 3 pairs which define areas of each triangles being equal. Now that each of the triangles are equal, when I combine all these 6 possibilities, triangle ABC equals triangle ABD, which in turn equals this, which in turn this equals this. Therefore, area of triangle ABC must be equal to area of triangle ABD, but area of triangle ABD, which in turn equals area of triangle ABE, and ABE equals ABF. Is how I see area of each of the triangles being equal. Therefore, if I have more than two triangles on the same base and between same parallels, all the triangles must have equal area, is how we understand the concept. So even if there are infinitely many triangles, they have equal areas if they are on the same base and are between same parallels. It's not restricted to two triangles, but more than two. It can be infinitely many triangles which can connect the same base with the line points on the line L, where all the areas will be equal, is how we understand. Infinitely many triangles on the same base and between same parallels are all equal in area, is how we conclude through the property. Now let's see area of triangle. What could be the formula for area of triangle? Just like area of rectangle is length into width, and area of parallelogram, which was recently proved as breadth into height or base into height, half. So we had area of parallelogram as base into height. Similarly, let's see area of triangle ABC. Triangle with its area. Area of triangle. Area of triangle is what we are going to investigate in the session. So let me take a triangle ABC. So ABC is a triangle. Now in this triangle, clearly I know that this is the base. And next, let me drop a perpendicular from C to AB, such that it cuts AB at D. So here the CD is the perpendicular which is called height. So this is the base and this is the height. So let's see how we can connect the base and height with area of triangle. In triangle ABC, AB is the base. And let me denote the base with some B. Denoted with B. And then I have CD, which is obtained by dropping a perpendicular from C. Drop a perpendicular from C to AB, such that it cuts at D. Therefore, here CD is the height, as clearly we can see. It is the height or the altitude of the triangle ABC. So I have base, which is denoted by B, and my height, which is denoted by H. So using the base and height, let's derive the formula for area of triangle. So with this being the base and this, I have my AB equals B and my CD, which equals H. Therefore, I can derive the formula as area of triangle ABC is given by the formula half into base into height square units. This is how we derive the formula for with the units unit square. So half into base into height is the formula for area of triangle, which can be reduced as half BH. Because my base is B and my height is H, is how we denote with half BH unit squared. Is what we get when we derive area of triangle ABC with the base B and the height H is half into base into height. So area of triangle is half base height, is how we understand the area of the planar region triangle, a three-sided closed region. Now let's get back to the previous same base theorem as discussed for triangles. The statement which says triangles on the same base and between same parallels are equal in area. Now the question comes, what would be the converse of the previous theorem? Will the converse hold? Is the biggest question. That is, if I say triangles which are on the same base and which have equal area, will the two triangles lie between the same parallel lines? Is what we are going to investigate in this session. Triangles connected with converse of the same base theorem. So let's see the converse. So my question which arises in the converse is, will the triangles on the same base and having equal areas lie between the same parallels? Is the biggest question I have here. So my arising question here for the converse is, will the triangles on the same base and having equal areas lie between same parallels? So with the condition that they lie on same base and they have equal areas, will the two triangles be between parallel lines? Is what we are going to investigate in the process. So let's see how we can understand this concept. Imagine I have the same base AB, and let me take a line L which is parallel to AB. Now let's take two triangles which are on the same base and having exactly equal area. So the planar region of the first triangle, let me take the triangle out here, and let me take the other triangle out here, which are on the same base AB. So here is the same base, and they are the same parallel lines. But now the converse says, but in the converse they are not parallel, but they are on the same base AB. So we have the same base, and the other condition is that the areas are equal. It is about proving that the two lines are parallel. So now we are going to investigate on whether the line L is parallel to AB. So in order that we have the same base, let's take this triangle the first triangle ABC, and the second triangle is ABD. Okay. So here the condition is that AB is the same base for triangles ABC and triangle ABD. So AB is the same base for triangle ABC and triangle ABD. Also, area of triangle ABC is equal to area of triangle ABD. These two triangles are considered in such a manner that they have equal area. Therefore, the two triangles chosen here must have equal areas. So with these two conditions, let's see if the two lines are parallel. Therefore, Converse states that L must be parallel to AB. So if the two triangles are with the same base and which are having equal area, they must lie between the two parallel lines, is what the converse says. So converse of the same base theorem is true to its justification. Converse holds for same base theorem. That implies converse holds true, is how we understand. So therefore, the triangles which are on the same base and having equal areas must lie between same parallels. They must be parallel. L parallel to AB, the same base, is how we understand the converse and its conclusion. Now that we have discussed the same base theorem on triangles and its converse, now comes the question on applications of same base theorem in solving many math problems. Today's session is about applications of same base theorem in real life. Applications of same base theorem. So let's see in brief about the applications of same base theorem. So here my question comes, find the area of the triangle ABD for the following diagram. So here I have a diagram in which I have to find area of triangle ABD. So let's see how we can find the area for the given problem. So here I have a diagram. Now here I have to find area of triangle ABD as clearly seen in the diagram. It is given with area of triangle with the dotted region is centimeters square. Now area of triangle ABC is given to be 14.6 centimeters square. That is, given area of triangle ABC is 14.6 centimeter square, and AB is the same base. So clearly I can see that triangle ABC and triangle ABD are on the same base. So here is the same base. And also they are between same parallels. So I identify here that AB is the same base. AB being same base, and the two triangles are between same parallels L and AB. Also, the line L is parallel to the same base. Same parallels. Now, striking with the previous same base theorem, these two are the two triangles which are on the same base and between same parallels. That is, therefore, triangle ABC and triangle ABD are the triangles on the same base and between same parallels. So triangle ABC and triangle ABD are triangles on the same base and between same parallels. Therefore, by same base theorem, we have area of triangles are equal. Triangles on the same base and between same parallels are equal in area. Therefore, area of this triangle must be equal to area of the second triangle. Area of triangle ABD or area of triangle ABC is equal to area of triangle ABD, are the two triangles which have equal areas. Therefore, I have this with area of triangle ABC, which is 14.6 centimeters square. So I have substituted for triangle ABC with 14.6 centimeters square. So 14.6 centimeters square is the area of triangle ABC, which indirectly states that the area of triangle ABD is 14.6 centimeters square, substituted with this. Therefore, the given question is to find area of triangle ABD. Therefore, triangle ADB has the area 14.6 centimeter square. Therefore, I can find the area of the other triangle using the area of the given triangle by using same base theorem. Same base theorem helps me in applying the concept in real life. As in the case of this example, I wanted to find area of this triangle, and I could do the area of this triangle by simply taking same base theorem. So my same base theorem gives me exactly the equal area as that of the previous, because two triangles on the same base and between same parallels are equal in area, and hence area of triangle ABD is equal to area of triangle ABC with 14.6 centimeters square. Therefore, the value of the area of this planar region ABD equals 14.6 centimeters square. Is how we understand the application of same base theorem in real life connected with same base theorem. Now that we have discussed the same base theorem for triangles and the same base theorem for parallelograms, now here comes even the applications which have been discussed further. Now comes the concept of combining a triangle and a parallelogram. Now let's investigate what if there is a triangle and a parallelogram with the same base and between the same parallels. How do we connect a parallelogram and a triangle is how we're going to discuss in the session. Same base theorem for triangle and parallelogram. Connecting triangle and parallelogram. Same base theorem. So let's see how we can connect a triangle and a parallelogram with the same base theorem. So here, let's see how we can understand the triangle and a parallelogram in the same base initially before we understand the theorem connecting them. So for a triangle and parallelogram on the same base and between same parallels is understood as the common base AB and the parallel line L which is parallel to this. And say I have a triangle out here, and next I have a parallelogram out here. ABC is the triangle and AB DE is a parallelogram. So here I have a parallelogram. So ABC is a triangle and ABDE is a parallelogram. So they are of course found to be on the same base and between the same parallels L and AB. Triangle ABC and parallelogram ABDE are on the same base AB, as can be seen here, and between the same parallels L and AB, that is the line L which is parallel to AB, is how we understand a triangle and a parallelogram on the same base and between same parallels. Now comes the question on the investigation of the areas of the triangle ABC and the parallelogram ABDE. Will the areas be equal, or is there any relation which connects area of triangle with area of parallelogram is the biggest question. Let's investigate area connected with parallelogram and triangle on the same base and between same parallels. Now let's state the theorem. Same base theorem for a triangle and a parallelogram. So statement. A triangle and a parallelogram on the same base and between same parallels. If the triangle and a parallelogram are on the same base and between same parallels, makes the area of parallelogram to be twice that of the triangle. So in such a case, we see that area of parallelogram is twice that of area of triangle. It is not equal, but area of parallelogram is twice or double of the area of triangle. So the statement is very clear with its statement, which says a triangle and a parallelogram on the same base and between same parallels make the area of parallelogram to be twice that of the area of triangle. Is how we understand the connection between a triangle and a parallelogram when they are on the same base and between same parallels. Let's see the property in brief. Suppose I have a same base AB and I have a line L which is parallel to AB. Now I have a triangle I have a parallelogram. So here is the parallelogram AB DE. So I have a triangle and a parallelogram between the same parallels and the same base. So here is the parallelogram. And here is the triangle. Is how we understand a triangle and a parallelogram on the same base AB and between the parallels L and AB. So the statement clearly says that for triangle ABC and for parallelogram ABDE, which are on the same base and between same parallels, area of parallelogram ABDE is twice of area of triangle ABC. That's how we understand the property of area of triangle and parallelogram. Why do you think is the area of parallelogram twice of area of triangle? How is the twice of the triangle connected? It's very simple, because a parallelogram is a four-sided figure obtained when its diagonal divides the parallelogram into two triangles. Say for example, I join the diagonal BE. So here I observe that there are two triangles between the diagonal, and we know that the two triangles are congruent in case of the parallelogram. A diagonal makes the two triangles to be congruent in a parallelogram is what we have learnt in the previous sessions. So if I have a diagonal, it makes area of this to be equal, or the diagonal bisects the diagonal of the parallelogram, divides the parallelogram into two equal areas. Is what we have learnt in the previous session. And therefore, when I cut the diagonal BE, I get two triangles ABE and BDE in the parallelogram ABDE, whose areas are equal. Therefore, this area equals this implies this would be twice of the added areas. And therefore, when I add this area with this, exactly two triangles on the same base are equal. So area of this equals area of this equals area of this. So A equals A plus A, which is 2A. So area of triangle equals twice. Area of parallelogram is twice of area of triangle, is how we get when each of the areas are equal. So therefore, this could be with the possible area of triangle ABC, which is equal to area of triangle ABE, which is equal to area of triangle BDE. All three areas being equal is how we get the three areas equal in this. And therefore, area of parallelogram ABDE is twice area of ABE, because the diagonal makes the two triangles congruent in a parallelogram. These two areas divided by the diagonal are equal, which is nothing but 2 times of area of ABE, which is equal to ABC. Therefore, area of parallelogram ABDE is equal to twice area of triangle ABC. That is, area of parallelogram ABDE is double or twice of area of triangle ABC. Therefore, we come to the conclusion that if there is a triangle and a parallelogram on the same base and between same parallels, which make, there must be with the condition that area of parallelogram makes exactly twice the area of the triangle, is how we understand the property connecting the triangle and the parallelogram in the same base theorem. Triangle connected with parallelogram to the same base theorem.